Balance the following combustion reaction. Now, without even looking at the reaction, it's a combustion reaction. So what are we going to assume is taking place? What's the basics of a combustion reaction? Okay, so we have some kind of a fuel. Most often in this class, it's going to be a carbon, hydrogen, and oxygen chain. And when I write that, does that ever confuse anybody? When I write that for the carbon, hydrogen, oxygen chain? See, what I'm kind of communicating there is it's a combination of carbons, hydrogens, and oxygens, and they're going to have all different kinds of subscripts. X, Y's, and Z's represent the various subscripts that could be there, you know? So a CH4, for example, would be a C1H4O0, right? There's no oxygen in it. So it's some kind of an oxygen, hydrogen, carbon chain. But usually carbon and hydrogen is occasionally oxygen in it as well. But if you just want to think of it generically as a fuel, combustion includes a fuel that is reacting with molecular oxygen to produce, and it always produces, in complete combustion, it always produces what? Right. Carbon dioxide and water. Most commonly, it's a carbon, hydrogen, oxygen chain in gaseous form that combines with gaseous oxygen, and it reacts to produce gaseous carbon dioxide and gaseous water vapor. H2O, gaseous water is water vapor. In this case, the following combustion reaction, we have COS2 combusts, okay, with O2. And not surprisingly, we have written down here CO2 O3 and SO2. Not following the form we're used to seeing, does it? Pardon? Mm-hmm. Here we've got, though it's shown as a combustion, this follows more the form of an oxidation reaction. We're not going to get into arguing if it is or is not combustion, okay? The problem has given us this and said this is a combustion reaction. It is something that reacts with oxygen. It may not be the typical complete combustion with a carbon, hydrogen, oxygen chain that we're used to, okay? But it's positing here, it's saying right here that balance the following combustion reaction. It's not saying, is this a valid combustion reaction? It's not saying, you know, anything other to qualify this combustion reaction. It's saying, this is a combustion reaction. So even if you looked at it and said, I don't recognize that as a standard combustion reaction, because it doesn't have a fuel that is a CHO chain, but it is something reacting with oxygen, so I know that it is a form of combustion, producing these products, not the same products I would expect, but all it's really asking then is to go through and balance it, right? So this is really, in essence, not anything from this module. This is just from the last module. This is balancing the equation. Let's look at it real quickly then. Hopefully I can do this quickly, short form up here. We could do the matrix, okay? And every time I say that, the matrix, I see these green lines coming down in front of my face, right? Remember from the matrix? So, but you know what I mean when I say the matrix, right? We could draw out, we've got cobalt, sulfur, oxygen, how many are on this side, how many are on that side, and work them all together. But I think we're at the place now, for the most part, that we should be able to visualize it and do this on the fly. Let's try it. How many cobalts do I have? Looking from left to right, I start with cobalt. It only appears once. How many cobalts do I have on the reactant side? Just one. On the product side, it appears only one time. And how many are there? 2. So I have to go from this many to this many. I have more on the product side than I have on the reactant side, so I need to increase a coefficient over on the reactant side. To get 2, so that I can have 2, I need to add a coefficient of 2. And now I'm balanced with regard to cobalt. Moving from left to right again, now I find my next element here is sulfur. It only appears this one time. And with the coefficient I now have, how many sulfur atoms are on the reactant side? Pause, delay, think. I have 4. And on the right-hand side now, looking all the way across, it only appears in this molecule. I have 1. So I start with 4. I need to end with 4. And I'm going to add the coefficient 4. So I'm balanced with regard to cobalts. I'm balanced with regard to sulfurs. The only thing remaining on the reactant side is oxygen, and it's in its molecular form, which means yes, because if I tweak this number, it doesn't affect anything else, right? Looking to the right-hand side, how many oxygens do I currently have on the right-hand side? Pause for a moment and think about it. All right, I have 1 set of 3 and 4 sets of 2. 1 set of 3 and 4 sets of 2 is 8. So I have a total of 11 oxygens on the product side of the reaction. Total of 11. Now looking to this side, I can source those 11 in sets of 2. So just think for a moment. How many sets of 2 do I need in order to have 11? Okay, 10 and a half. So I'm going to write it up here. It's not really a superscript, but I didn't leave enough room for it. So I have 10 and a half O2 molecules. That would be my balanced reaction. Okay, 10 and a half, right? Oh, excuse me, 5 and a half. Right. Thank you for the inquisitive look. And I'm not working off an answer guide. I'm doing it live with you. So here we go. 5 and a half sets of 2. That makes sense. 5 and a half times 2 is 11, and I'm looking for my 3 and my 8 makes 11. So, while it's proportionally correct to say that 2 of these molecules and 5 and a half of these molecules react to produce 1 of these and 4 of those, it's not in its appropriate form, right? We write these equations, these balanced equations, with whole integer coefficients. So we need to get rid of the fractional coefficient. In this case, the only fractional coefficient is 5 and a half. It's 11 halves, right? I could do that, right? 11 halves, 5 and a half is 11 halves. Either way, whichever way you look at it. But I have a coefficient that is a half. How do I eliminate the fraction? Well, I can multiply the whole thing by a number. And that number, surprisingly enough, is going to be the denominator of my fraction. In this case, it's 5 and a half. If I multiply everything by 2, I'll eliminate my fractional coefficient. So multiplying the whole thing by 2 produces 2 times 2 is 4 COS2 molecules, and 2 times 5 and a half gives me 11 oxygen molecules that react to produce 2 of the cobalt oxygen on the end and 8 SO2 molecules. So 4 and 11 produce 2 and 8. Did I make any errors, or are there any further questions on balancing this equation? Are you all comfortable? This is you can answer immediately with the head bob, okay? Are you all comfortable with now doing the balancing on the fly using fractional coefficients, then multiplying it out to eliminate the fractional coefficients? Okay, good. Thank you. Question, and this was question number 1 from EPP Module 7, okay? Go ahead and erase this. Number 2 says, what's the balanced chemical equation for the formation of C2H4O? Okay. What's the balanced chemical equation for the formation of, and they give you a molecule. Now, generically speaking again, when we're doing a formation reaction, the way I've written it in here generically is, what does a formation reaction look like? Again, generically using A, B, and C. Correct. I've used A plus B plus C reacts to produce A, B, C. A formation reaction is a reaction which produces a molecule by combining the elements that form that molecule. There's no additional product. There's no excess reactant. It's a perfect balanced combination to build up a particular molecule. In this case, the molecule that we're building up is C2H4O. C2H4O. So looking from left to right, I would go through and write down all the different elements that are in this molecule. Starting from left to right, I've come up with, first of all, carbons. Second of all, hydrogens. And lastly, oxygens. Joe. Because this could be one of my fuels. Remember with the combustion, generically speaking, a carbon, hydrogen, oxygen chain. This could be my fuel for further combustion later on. Right now, carbon, hydrogen, and oxygen make up this molecule, and so I need to represent them, carbon, hydrogen, and oxygen, in the reactant side in order to put this molecule on the product side. That's the first step. You're gonna write down the elements that combine to form the molecule. Second step, don't answer right away, but second step, what do I do now? My second step, every time we've done one of these problems, we've always done the same second step. And that second step is, drum roll, yes ma'am, check and annotate the homonuclear diatomics. What we're saying is we're going to look, because most atoms form in their elemental form, their atomic form, as a single atom. The exceptions being the homonuclear diatomics. Remembering that the homonuclear diatomics are hydrogen, looking over here, hydrogen, nitrogen, oxygen, and the column 7 elements. So what you need to memorize is hydrogen, nitrogen, oxygen, and that whole column. If you find those elements in your reactant side, you need to annotate them by giving them the subscript of 2, because those atoms, those elements, naturally occurring, they will form molecules by combining with another atom of the same type. Again, looking at my reactants, is carbon a homonuclear diatomic? No, it's not. Hydrogen? Yes, it is. I need to annotate that with a subscript 2. And third, oxygen. Is it a homonuclear diatomic? It is. I annotate that with a subscript 2. So first step, write down the elements. Second step, annotate the homonuclear diatomics. Now third step, I'm going to start balancing the reaction. And it's easy because I'm looking for these numbers, and whenever I make any adjustments to my coefficients over here on the left-hand side, I don't mess with anything else. They're all just the elements. So it's pretty straightforward. Now I say in here often, you cannot mess with the subscripts, right? But when you actually annotate them as homonuclear diatomics, you're not messing with them. You're accurately depicting what they actually are. So this isn't messing with subscripts. On this next step, once we've established where the homonuclear diatomics are, now you can no longer mess with the subscripts. Now it's all coefficients. You've got to do all the balancing with coefficients only. And so looking on the left-hand, right-hand side, I look at my carbons. I need to have 2. And in order to have 2, I need to have 2 originally to start with, right? And the only way to get 2 is to add the coefficient of 2. These 2 carbon atoms will then be brought together in the molecule. Hydrogen. I need to have a total of 4, and they're going to be coming to me in sets of 2. So how many sets of 2 do I need in order to have 4? I need 2 sets. And the oxygens. In my molecule, I need 1 oxygen atom. And they're being delivered to me in sets of 2. So how many sets of 2 do I need in order to have 1? Just 1/2. So 1/2 of 2 is 1. See, now I have no extra, I don't have any extra oxygens, hydrogens, carbons. Nothing of my reactants is left over. It's all being used. And that's the balanced equation. An unbalanced equation would have extra reactants or extra products, or you would have stuff all over the place, okay? It wouldn't be balanced, wouldn't be true. We're trying to make sure that this is true, so we have nothing. So the left-hand side has to perfectly match the right-hand side in both its mass and in its count of the individual atoms. Same problem we had last time. What's that problem? Someone, what's the problem? Yes, sir? Fractional coefficient. Good. This might be true, but it's not correct because we cannot, by convention, we're not going to depict it with a fractional coefficient. So we need to multiply all the coefficients by something to get rid of the fraction. And in this case, we only have one fraction, and that fraction has a 2 in the denominator. I'm going to multiply the whole thing then by that denominator of 2. Multiplying everything by 2, I then have 4 carbons and 4 hydrogen molecules and 1 oxygen molecule that reacts to produce 2 C2H4O. Check it real quick. 4 carbons, 4 carbons. 8 hydrogens, 2 sets of 4 hydrogens is 8 hydrogens. 2 oxygens, 2 sets of 1 oxygens is 2 oxygens. My counts match. Now, because we had to multiply up, it shouldn't be an issue, but we can just always give a real quick check and say, are there any common factors here that we can reduce the coefficients again? No, we have got a coefficient here of 1, so we're not going to reduce it at all because that would take us back to a fractional coefficient. But if they did have a common factor, we would factor that out and reduce the coefficients to get them in their simplest form possible. Checking with the book. Book says 4 carbons, 4 hydrogen molecules, and 1 oxygen molecule react to produce 2 of the product molecules. So this is correct. Okay? Any general questions on this balancing this formation reaction? Again, the only piece of information they gave us was balance an equation for the formation reaction of this molecule. Since it's formation, we break it down into its elemental components. And then we annotate those if they're homonuclear diatomics. And then we balance the atom counts. And then if necessary, we multiply in order to eliminate fractional coefficients. It's the same process every time you do a question like that. All right, number 3. What is the balanced chemical equation for the combustion of C16H34? The combustion of C16H34. Now, hopefully you see, first of all, that this is, well, start with combustion. When you see the word combustion, what do you know is the other reactant? Oxygen. Good. This is the fuel that's reacting with oxygen. Whatever it is, it's going to react with oxygen. Second of all, I'll take a look at it and see, do you recognize this as being a CHO chain molecule? It's a CHO. The CHO is, it's a C16H34O0. There's none of it, right? It still fits within the CHO kind of paradigm. Right? It's just that there is no oxygen. The Z subscript there is 0, so it doesn't appear. So carbon-hydrogen or carbon-hydrogen-oxygen chain molecule reacting with oxygen. It's combusting with oxygen. So what are the products of this combustion reaction? We've had 2 of them every time. With a carbon-hydrogen-oxygen chain combusting, reacting with oxygen, the product of reaction is going to be carbon dioxide and water, CO2 and H2O. So we can write all of this just by them telling us it's the combustion of this molecule. We know enough now to complete the rest of the basic chemical equation, basic reaction formula. Doesn't mean it's balanced. It just means now we've got all the pieces we need to look at. So what is the balanced equation for that? Now we've got all the components, all the reactants, and all the products. Now we can go through and start our balancing again. Continue to use the short form. Starting from left to right, carbon, hydrogen, oxygen all appear once, and they appear carbon once, hydrogen once, and oxygen in 2 places. But again, because it's elemental oxygen over here, I'm going to save that for last because it's my cleanup, right? If my last thing I do is balance the oxygens from the reactant side, I can add a coefficient here and it doesn't mess up my carbons and my hydrogens. So I save it for last. Looking from left to right again, I've got 16 carbons, and over here I have 1 carbon. I have to consume all 16 for it to be balanced. So how do I get rid of 16 carbons one at a time? Well, I need to make 16 sets of whatever molecule uses that carbon. I can only consume them by 16. So here I've got 1 set of 16, and here I have 16 sets of 1. Now my carbons are balanced. Does everybody see that? 1 of 16 is equal to 16 of 1. Second element, my hydrogen, appears once here and once here. I have 34 hydrogens that need to be consumed. And by looking over at my products, 34 of them consumed in sets of 2. How many sets of 2 do I produce if I start with 34? 17. 17 sets of 2 will be 34, and we'll consume all 34 of those. Okay? So my carbons are balanced. My hydrogens are balanced. Now it's just a matter of cleaning up with the oxygens. I know that I'm going to have more on this side. It should be obvious now looking at the coefficients and the subscripts. I've got a lot more oxygen being depicted on my product side than I have on my reactant side. So let's do a count of oxygens on the product side of reaction. I've got 16 sets of 2, which gives me a total oxygen count of 32. And I have 17 sets of 1 for a total of 49. I have 49 oxygens being depicted on my product side. So I need to have 49 on my reactant side. Okay? And they're coming to me sourced in sets of 2. So how many sets of 2 do I need in order to have 49? Well, I take that 49, cut it in half, right? It's going to be 24 and a half. 24 and a half. I'll move my plus sign over a little bit, give myself some room here. I think after all these years I'd remember to do that, but I never do. Which is why I use pencil, not pen, for chemistry, for the most part. Okay, so now I have a true statement. This is true. We can go through real quickly and just kind of make sure. But we also know that if we've got a fractional coefficient, we can't leave it like that. Okay? Looking at the coefficient that's fractional, its denominator is a 2. So by practice, I'm going to go ahead and multiply everything by that denominator. Multiply everything by 2. And I'm going to end up with 2 C16H34 plus 49 again. 49 O2 reacts to produce 32 CO2 and 34 H2O. Now let's check it. 2 sets of 16 is 32. 32 sets of 1 is 32. 2 sets of 34 is 68. 34 sets of 2 is 68. 49 sets of 2 is 98. Over here, I've got 32 sets of 2, which is 64. 32 sets of 2. And I have 34 sets of 1. It's 98. So my atom count is balanced. I've got the same number of carbons, hydrogens, and oxygens on the reactant side as I have on the product side. Then I need to take a step back, just as part of my standard practice in solving these, look at my coefficients and see if I have any common factors. that can be applied so that I can reduce it down. And again, since we had a fractional and had to multiply up, that's probably not going to be the case. But I still do it as a check anyway, you know. But there are no common factors between these. And so this here, 2 and 49 react to produce 32 and 34, is the balanced equation for the combustion of C16H34. You see in the pattern, the steps we're doing? First of all is writing a form of the equation. Decomposition, combustion, formation. One of those standard 3 types of equations. Writing the products of the reaction, you know, getting the whole equation down based upon what type it is. And then we're just balancing it, and then we're multiplying it, we're checking for factors. It's the same process after that. Once we have the equation written down, all 3 are actually 4 when you talk about burning metals, and then 5 if you talk about incomplete combustion. It's the same process though. The first is to write the equation. What kind of reaction it is helps you write the equation. Then after that, the second step, the third step, and the fourth step are exactly the same for every type. So, as I hopefully will remember to ask after every question, are there any questions on the combustion of a carbon, hydrogen, and oxygen chain molecule? Because given this, you'd be expected to know that it produces these, then balance it. All right, moving on to a different type of question. Number 4 says, what's the mass in kilograms of a mercury atom? Mercury atom in kilograms, number 4. The mass of a mercury atom in kilograms equals what? Mass of a mercury atom in kilograms. Now, I'm going to go over here to the aside for just a little bit. Okay? We need to find, for mercury, it's got a unique mass. Agreed? Each element has its own unique number of protons, neutrons, and electrons. Each one has its own unique particular mass. We're going to need to find a source that's going to tell us the mass of a single mercury atom. That source is going to be our periodic table, right? So go to your periodic tables in the front of the book. Take a look for mercury. What's its atomic number? For those of you that have found it? 80? Correct. It's a column 2B element. 80 is the atomic number, 80. Okay? Now looking in your book there, it gives us another number. 80 is the atomic number, that's the number of protons. The other number is its atomic mass, and that number is what? 200.6? That's the second number, right? We've already said that that number represents the atomic mass of that element. For every element in there, the top number, the way it's depicted in this table, the top number is the atomic number, the bottom number is the atomic mass. The atomic mass for this element is 200.6. But it's left off units, and we all know, right, that an answer that's a number without units is meaningless. 206 peanuts, 200.6 elephants, 200.6 pounds, 200.6 what? 200.6 something. Now, because we pulled it off the periodic table and we're looking at individual atoms, what are the units that this 200.6 represents? Yes, sir. AMUs. So the mass of a helium, one helium atom is 200.6 AMUs. That's the scale for the each. The scale for each is a unit of an AMU, an atomic mass unit. An atomic mass unit is 1/12 of the mass of a carbon-12 atom. That's how they came up with that number. But it's 200.6 somethings, and because we're talking about individuals, it's an AMU. 200.6 AMU. Now, this question doesn't have anything to do with moles. Okay, some of you right now like to, okay, we're going to multiply something by Avogadro's number and get into moles, right, to figure that out. Actually, take 1 and divide it by Avogadro's number and take this in grams and do some math like that. That's making it too hard. You've added a step there because you've been given another statement of equality when it comes to converting between AMUs and grams, right? What is that equality? That a certain number of AMU is equal to a certain number of grams. Yes, sir. Correct. We have a statement of equality for this module that takes us and helps us convert between AMUs and grams. Avogadro's number does not come into this problem at all. It is. That's what I'm saying. Knowing this conversion, it doesn't come into it at all. However, this number is the inverse of Avogadro's number. This number is 1 divided by 6.02 times 10 to the 23rd. Okay, that's how this number comes about. But if you start thinking about, I need to use Avogadro's number, some of you get led astray and end up far from your correct answer. The simpler, more direct route would be to say, I have a statement of equality that relates AMUs to grams. Let me use this, because knowing this statement of equality, I know if I am given AMUs, I can get to grams. Right? If I'm given 200.6 AMUs, and I'm not asked for AMUs, I'm asked for kilograms, well, let me first of all go to something I can get to quickly, and that's let me get this in the language of grams. Let me get out of the language of AMUs, let me get it into the language of grams. And on our diagram before, we did this generically, we talked about the number of pieces and the number of moles and then the mass, and if you follow that diagram, that's why you go from pieces to moles to mass. That kind of a diagram will lead you in that process, and you will get the right answer, but you're adding a step that is unnecessary when you know this statement of equality. So let's go ahead and use that statement of equality to take this number and let's translate it into grams. So what I encourage you to do is just start with the units. If you just do the units and then plug in the numbers, but if you check the units first and you get the correct ending units, then filling in the numbers is easy. And then plugging them in your calculator is easy. It's this setup that I'm about to do which is actually the hard part of this problem. Make sure you get it right. Make sure the logic makes sense to you. And so I'm starting with my units are AMUs. And I want to convert that into something that I know is going to have AMUs in the bottom because I don't want to speak that language anymore. I want to eliminate AMUs from my answer. I need something that takes me from AMUs to grams. Well, the problem doesn't ask me to solve in the language of grams, right? It asks me to solve in the language of, or in the units of, kilograms. So if I do this, do you see that my answer is going to be in grams? AMUs, and when you have a number here, it's the same as writing that same thing all over 1, if that gets confusing to you. And that'll help you see that, hey, this AMU is in the numerator, this AMU is in the denominator, and I know then that that would cancel that and leave me with that. But that's not what I'm asked to solve for. I'm asked to solve for kilograms. And in order to solve for kilograms, I need to get rid of grams. Okay? So we check the setup. AMUs cancels AMUs, left with grams. Grams cancels grams, and I'm left with kilograms. My answer is supposed to be in kilograms. It checks. My setup now is right. This is the hard part, the setup. AMUs, grams per AMU, kilograms per gram gives me kilograms. Now let's plug in the numbers that we know. We're starting with a given of 200.6. 200.6 AMUs. Now the rest of this are all conversion factors. I need some relationship, some true statement of equality that relates AMUs to grams, and I'm given this one. Well, that's great. 1 AMU is 1.66 times 10 to the negative 24th grams. And if I did this math right here, my answer would be in grams. But to get it into kilograms, I need to take it one more step. I need something that relates grams and kilograms. And one of our most basic statements of equality within the system is that 1 kilogram is equal to 1,000 grams. Right? So now I have the setup with my actual numbers in it that I need to calculate. And so 200.6 times 1.66 times 10 to the negative 24th, that whole thing divided by 1,000 is going to give me my answer in kilograms. And it's 3.33 times 10 to the negative 25th kilograms. That's what the key says. I haven't actually worked this out, but the key tells me that that's the answer. But let's look at it real quickly, see if it makes sense ballpark-wise. I've got 200 times a little bit more than 1.5, right? I'm just estimating here. Let me just see if my answer is anywhere in the realm of possibility. I have 200 times 1 and a little bit more than 1.5. So 1.5 times 200 would be 300. I got a little bit more than 300 then, right? 200 times 1.66 is a little bit more than 300. So my answer here, I can see in there, hey, could it be 333? Okay. And my scientific notation, 333 divided by 1,000, well, let's say it's 333. Let's just say that that does work out to be the math part of it, 333. Now my scientific notation, I have times 10 to the negative 24th divided by 1 times 10 to the third. This one right here, see? All right, does that make 333? 333 divided by 1, let's just leave it as 333, times 10 to the, when we do this, we have a exponent in the denominator. When we're dividing by, we actually then subtract it from the top. So it's negative 24 minus 3, or 333 times 10 to the negative 27th. Okay? But we don't have this in the right format. We need to put it in integer, decimal, in this case 3.33. I move the decimal 2 places to the left, which means I need to make this 2 numbers higher. 2 higher from negative 27 is negative 25. You see? Now, I wouldn't necessarily expect you all to be able to do that. I hope you would be able to do that, but the problem didn't ask you to do that. So don't get overwhelmed if you're going, I don't see how you estimated that. Okay, that's just my way of checking it. That's kind of like on the math test where you solve an equation for x, and then you go on to the next problem. Well, if you have time, you can stop and go, wait a minute. If I've solved for x, let me plug x back into the equation and see if it comes out to be true. And if it comes out to be true, I know I've got the right answer. Okay? In this same way, being able to estimate what your answer should be about, and then looking at your answer and going, yeah, you know, if I came up with 3 times 10 to the negative 25th, and it's 3.33 times 10 to the negative 25th, I feel pretty comfortable my answer is right, because it's really in the ballpark. You might look at it and say, but it's only off by 1 number here. Maybe you had times 10 to the negative 26. Well, guess what? You're not off by 1, you're off by a factor of 10. And if your number's off by 2, you're off by a factor of 100. It's more than just off by 1. It's off by a factor of 100. And that can be pretty big. Okay, so that's number 4, EPPs, number 4. Okay, yes, sir.
So which direction do you move in the decimal to make it subtract or add?
When you have, let's say you have a number that's ABC times 10 to the third, okay? Let's say it's in that form. The implied decimal place is right here. You agree? Okay. My format of my number has to be A decimal BC. That's appropriate scientific notation. times 10 to the something, right? Now, when you make one side smaller, if you're trying to keep the same value, well, I'm trying to say the same value and represent it in another way. To take this same value here and move it to this one. Do you see that this number A, let me use a real number. I'll use 1, 2, 3 just to make it easy. Let's say we have 1, 2, 3. 123 times 10 to the third. I recognize that I'm supposed to write it in appropriate form, which would be 1.23. I see that the coefficient should look like this. Ask yourself this question. Who's knocking at the door? I know. I just finished with, ask this question. Who's knocking on the door? Okay, so we have 1.23 times 10 to the third. I need to represent that same exact number. I'm not changing its value. I need to represent it in appropriate scientific notation format, which needs to be a integer, decimal, integer, however many more numbers you have, right? Based on the significant figures. So this needs to be represented by this. Tell me, is 1.23 smaller or bigger than 123? It's smaller. So if I make this smaller, I need to make this bigger. See? For it to be the same value, if I make my integer, or if I make my coefficient smaller, I have to make my notation larger for it to be the same value. Since it went from 123 to 1.23, I've made it smaller by a factor of 1, 2. I've made this side smaller by a factor of 2, so I need to increase this by a factor of 2. 10 to the third, increase it by 2, makes it 5. See? So when you make the front small, you have to make the tail big for it to be the same. Conversely, the other way, if I was going the other way, let's say my answer was 1.23 times 10 to the fifth, and I was asked to put it in times 10 to the third, I would represent this number, I would move it over 1, 2, so I make it bigger by a factor of 2, which means to keep it the same value, I have to decrease this by 2. Okay? That was second bell. That was, so we're end of passing, right? Okay, so this is the point where, let's go ahead and take a break. If you're going over to Mr. Patty's class, you're dismissed. You can go head over there. If you're staying here, just take a couple-minute water break, and when you're all back in, we'll keep going. Number 5. I'll ask this class, do you want me to go through number 5? It's basically, sure, thank you. If you'd like me to go through number 5, I will. If you want me to see if we have time at the end to go back to it, I will, because it's the same type of problem as the one we've just done, but rather than using an atom, it's using a molecule. You want to do it this one? Okay. So number 5 says, what is the mass in grams what is the mass in grams of a lithium carbonate? What is the mass in grams of a lithium carbonate molecule? So what is the first step in solving the problem? If we were looking at an atom, let's say we're looking at lithium, we would go to the periodic table, we'd find the mass of an individual lithium atom. In this case, we're not asked for an atom, we're asked for a molecule. Asked for a lithium carbonate molecule. So we go back to this issue of, do you remember your polyatomic ions, right? Because we're making a lithium carbonate. We've got lithium, right? And we have the carbonate. Lithium carbonate. Now, this still isn't correct, right? Because lithium, first of all, you got to remember, what are the different charges? We're forming an ionic bond. It's a polyatomic ion that's forming an ionic bond to form this molecule, right? So lithium, where's lithium on the periodic table? It's a column 1 element. So just because it's a column 1 element, you see that's the very first column on your periodic table. So lithium wants to have a charge of what? It's column 1 means it has 1 valence cell electron, and it would rather get rid of 1 than try to fight to get 7. So lithium, when it loses the 1, is going to have a charge, ideally, of 1 positive. Carbonate is a polyatomic ion, and that polyatomic ion has a charge of 2 negative. Good. So it's a 1 positive ion, lithium ion, and a 2 negative carbonate ion. So when they form to produce a lithium carbonate molecule, remember we're going to ignore the signs, cross, and make them subscripts. So it's going to be a lithium 2 CO3 for lithium carbonate. Okay. But do you remember now how to do it? Lithium, column 1, plus 1, carbonate, 2 minus. Now, see, what we're saying here is we need 2 lithiums to balance 1 carbonate. If we had 2 lithiums, it would have a 2 positive charge. The 2 positive charge balances the 2 negative charge and forms 1 molecule that's neutral for lithium carbonate. So now we have our molecule, lithium carbonate. So what's the mass of this molecule in grams? Well, process-wise, if you're given a single atom or molecule and you need to compute the mass, we're always going to start with AMUs. Because AMU is at the scale of the individual piece, the individual atom or the individual molecule. It's going to be in AMUs. So we're looking at lithium. Bless you. It's going to be on the internet forever. This is Brandon sneezing. Okay. Lithium, looking in the front here, it's got an atomic mass of 6.94. 6.94 AMUs per atom. And in this case, my molecule has 2 lithiums, which means I need to account for 2 times the mass of my lithium. Okay. There's my lithium. Next, I need to account for the mass of my carbons. I haven't done it quite this way before, so it's a little bit different way of thinking about it, but if it helps you understand it, awesome. 2 lithiums, now I need the mass of 1 carbon. We go back here to the mass of 1 carbon, and not surprisingly, mass of 1 carbon is 12, because 1 AMU is 1/12 the mass of a carbon-12. So the mass of the carbon is 12, and then I need to consider the mass of my oxygen. Now I have 3 oxygens, and the oxygens, according to the periodic table, should be 16. It is 16.0. And one of the encouragements in the text, I believe it was in this text, is you could do 2 times and 3 times, but if you think about it in terms of adding it up, it's cleaner in terms of precision and everything like that, because we're not going to be able to carry over into we're only going to be able to go into the tenths place here, not the hundredths place, in terms of precision when we do adding and subtracting, right? Precision is to the least precise, and here the least precise is going to be in the tenths place. Let's do the addition. 4 and 4 is 8. 9 and 9 is 18. Carry the 1. So it's 6, 6, 12, 13, 14, 15, plus 18 is 33. Carry the 3. 3, 4, 5, 6, 7. 73.88. And because our precision here is to the tenths place, I look to the hundredths place to determine if I round up or leave it the same. It's 5 or greater, so I round up, and it's 73.9 AMUs. That mass, 73.9 AMUs, is the mass of one lithium carbonate molecule in atomic mass units. And so just like the last problem now, we're asked not to put it in AMUs. The question asks us to put it in grams. And in the text, it gives us again the conversion factor of 1 AMU is equal to 1.66 times 10 to the negative 24th grams. So there's my statement of equality that I can use to build a conversion factor. Next step. Just in your own mind, think about it for a moment. What is the next step? Now that I have my mass in AMUs, what do I need to do now? So what we need to do now is to translate it, right? We're going to convert it from the units of AMUs and get it into the right units we're asked for. We're asked for grams. And we have a statement of equality here that gives us the translation from AMUs to grams. So taking our answer in AMUs, I've got 73.9. Let me take it back just a moment. Let me step back and say, I want to encourage you to use this process. Go through and check your setup first by checking the units. I know that I've got an answer right now that's in AMUs. And I know that I need to convert it from AMUs to grams to get my answer in grams. That's my setup. My known multiplied by my, if possible, my ending units divided by my known units. That's my setup. Now let's go through the setup. Is it correct? Yes, it is. AMUs cancels AMUs. It leaves grams, and that's my answer, so it checks. Now I'm going to go through and actually put in the numbers that belong here in the setup and then do the math. We know that we have 73.9 AMUs, and we know from this statement of equality that 1 AMU is 1.66 times 10 to the negative 24th grams. The key is telling me here that my answer is going to be 1.23 times 10 to the negative 22nd grams. Okay. And again, I could go through and see if it's ballpark right, but again, that's outside really the scope of this course. That's a math ability. I don't want you to dwell on that. I want you to, first of all, get the setup right and do this. And if you get the setup right and the math right and the computer skills or calculator skills right, you'll get the right answer. Being able to approximate your answer to see if it's approximately correct is, I would say at this point, an advanced skill for you all. Okay, so don't worry about that. If you understand it, do it. But if you don't worry about it. Don't stress about not knowing how to do the estimated answer, is what I'm saying. So 1 lithium carbonate molecule has a mass of 73.9 AMUs, which is also equal to 1.23 times 10 to the negative 22nd grams. All right? Yes, sir?
How would you put it, like, in the calculator or whatever to get the 1.23? Like, whenever you times in it, to get it.
When you multiply it, what? The 73.9 and the 1.66. Each scientific calculator is a little bit different. I'm not sure how yours handles the scientific notation. So you go ahead and try it now. Do you know how to enter exponents into your calculator? Okay. So you're just going to multiply 73.9 times 1.66 times 10 to the negative 24th. When you multiply those two together, it should give you this answer. When it's divided by 1, of course, you can just not worry about that. Dividing anything by 1 is itself, so those all drop out. So we go to number 5 then? Okay. I'm assuming we'll just press on sequentially then? Okay. Number 6. How many moles of H2CO3 are in a 1,250 gram sample of the compound? So So my sample mass of H2CO3 is equal to, let me write this, my mass of my H2CO3, my sample, my whole thing, is 1,250 grams. My moles of H2CO3 is what I'm asked for. A sample of H2CO3 has a mass of 1,250 grams. How many moles of H2CO3 is in the sample? So in our generic bridge diagram, remember we had moles. We have an upper and lower translations, which we're not using this module. We will in the future. Over in this direction, we went to mass, and in this direction, we went to pieces, or the count. All right. Now you see up here, we have a mass, which means in this problem, we have a mass, and we're actually moving this way to find moles. I'll be consistent with the way I drew it in previous lectures and do it that way. Okay? So we're going from, in this case, we're going from mass to moles. In this case, we are following this path from mass to moles. Now the key to translate from mass to moles, I've got some information that needs to be in the middle there. Some translational key that takes me from mass to moles. And if you remember from this diagram, that key is what? Does anybody remember? The molar or mass, right. The atomic mass or molar mass. In this case, since we're going to mass to moles, it's the molar mass. Sometimes I'll just abbreviate it MM. But the molar mass. The molar mass is what I need to know in order to go from mass to moles. The molar mass, because I'm looking at a mole, I'm looking at scale-wise, not AMUs, but grams. I'm not looking at the pieces, I'm looking at the larger whole. To go from, in this case, a mass to moles, let's make sure we do it right. Are we going to multiply by the molar mass, or are we going to divide by the molar mass? Divide by. Very good. So in this case, it's divided by the molar mass. Let's see if that makes sense, because I'm going to have grams divided by the molar mass, which is in the form of grams per mole. And so grams divided by grams per mole, I hope you would know that that is the same as writing grams times the inverse of my denominator, which is moles per gram. And then the units cancel out to give me moles. So I know that dividing by the molar mass is the correct operation. That's what I need to do. All right, so to go from mass to moles, I need to figure out the molar mass of whatever it is I'm looking at. And what I'm looking at here is an H2CO3 molecule. So I need to I need to calculate the molar mass of an H2CO3 molecule. We're good on that. The mass of the molecule is equal to the mass of the sum of the elements that make up that molecule. The mass of the whole is equal to the sum of the mass of the parts. Okay? So, what are the parts that make up this molecule? What different elements? Well, I've got hydrogens, carbons, and oxygens. I've got CHO. Everything that makes it up is either carbon, hydrogen, or oxygen. So, I'm going to need the masses of all the individual pieces. I need how many hydrogens? I have 2 of them. The mass of a hydrogen, if you looked at your periodic table, is 1.01. And I need 2 of them. Carbons, we've already done carbon, and carbon is 12.0. And oxygen, we've already said, is 16. And I need 3 of them. Okay? Is everyone clear on the setup? Yes, ma'am. Oh, thank you. I was counting up. So 1.01 two of them, 1 carbon and 3 oxygens. And do you see how I'm accounting for the mass of everything that makes up that molecule? So the mass of the molecule here is going to be the sum of the mass of all of the pieces that make up that molecule. We'll go through and do the addition. First of all, make sure you don't get your columns mixed up. These are in the tenths and the hundredths place. I have 2 in the hundredths place. Adding up all the tenths places, and I still get 0 because there's nothing there. Then adding up the ones place, it's 1, 2, and 2 is 4, plus 18 is 22. Carry the 2, 3, 4, 5, 6. 62.02 AMUs. 62.02 AMUs. Now, I need to look in terms of my precision. My least precise, they're in the tenths place. So I look at my answer in the tenths place, I look to the right to the hundredths place, and I find out if it's 0 to 4, I leave tenths alone. If it's 5 or higher, I up this 1. In this case, it indicates that I don't do anything, so I just eliminate that. 62 grams, or excuse me, 62 AMUs is the mass of 62 AMUs is the mass of 1 molecule. 1 molecule. Okay. Now, the molar mass is not the mass of 1 molecule. The molar mass is the mass of 1 mole. So my procedural step here is, I know the mass of 1. What is the mass of a mole? Mass of a mole, all we're going to do is keep the same number. The mass of 1, and so 1 mole, the mass of 1 mole, if this is the mass of 1 molecule, mass of 1 molecule is 62.0 AMUs, then the mass of 1 mole of that molecule is equal to 62.0 grams. This is the statement that we need to understand in this process step all the time. We find the mass of 1 molecule or 1 atom, if we're talking about a single atom, but in this case we're talking about a molecule. So we'd find the mass of 1 molecule in AMU, and then we know that the mass of 1 mole of that molecule is equal to that same number with a different unit, and that unit is grams. So the molar mass in this problem, the molar mass is equal to 62.0 grams per mole. I have been given a mass of 1,250 grams. And as we said before, I'm going to take the mass, divide it by the molar mass, which is 62.0 grams per mole. And that's going to equal, let me check my units, grams divided by grams per mole is the same as grams times mole per gram. Yes, my units are going to be moles, so my setup is correct. And then I do the math. 1,250 divided by 62. The key tells me that the answer is 20.2. 20.2 moles of H2CO3. Process again. I have the molecule. I find the mass of 1 molecule in AMUs. I take the mass of 1 molecule in AMUs, and I change its units to give me the mass of 1 mole in grams. With the mass of 1 mole in grams, I take the mass that I've been given. When I go from mass to molecules, I divide by the molar mass, the mass that I was given divided by the mass for 1 mole, which is the molar mass, and that produces a result which is my answer in moles. Again, steps, each step in itself is not all that difficult, just to do the steps correctly, in the right order. In this case, there is an order to them. You have to have it in the right unit, this set up to get AMUs and then know that it's the same number but converted to just changing the units to grams to get 1 molar, the molar mass of that molecule. Carry on. Any issues, questions, difficulties with this one? Okay. It's not difficult to compute the mass of one molecule. It's just to remember that that is also the same as the mass of 1 mole if the units are changed to grams. And then make sure that you've got your diagram memorized correctly, that you're taking the mass divided by the molar mass to get your answer. Number 7. It says, what is the mass of a calcium chloride sample What is the mass of a calcium chloride sample? Massive calcium chloride sample if it contains 0.344 moles. Okay. What is the mass of a calcium chloride sample if that sample contains 0.344 moles of calcium chloride? Again, we're going to be using the same bridge diagram. And this time we don't know the mass, but we know the number of moles. And so we're going to move from moles to mass. What's the operation going to be? Multiplication. Remember, if you can figure out one of them, you can figure out all of them. Because written this way, with the arrows left, left, and then, or excuse me, right, right on the top, and then left, left on the bottom, once you figure out one of them, it alternates back and forth, right? So it's multiplication, division, multiplication, division. If your arrows are all pointing in the same direction on the top and the same direction on the bottom. That's what got it messed up on the one that I took off the internet. That was an error before, is they had their arrows in different directions in the same signs, you see? So it's got to be to the right is divide, multiply, to the left, divide, multiply. If you lose track of it, if you can solve one of them, if you say, hey, I know that this one is going to be multiply, then you know it's multiply, divide, multiply, divide. So write that down. That's your key for answering these kind of questions. We've got a mass is equal to what when the moles are equal to that number of moles. Okay. So I'm going between these two languages. I sometimes use that. I'm going from the language of mass to the language of moles, and I need a translator. The translator between these two languages is going to be my molar mass in some form. So we need to compute the molar mass. What is the molar mass of calcium chloride? Well, the mass of calcium chloride is going to be equal to the mass of the calcium in it, which we have just 1, and the chlorine, which we have 2. So the mass of calcium, periodic table, it's column 2A element, atomic number 20, mass is 40.1. So calcium here is going to be 40.1 AMUs for 1 calcium atom. And chlorine should be 35.5. It is, say. Chlorine is 35.5. And we need 2 of them, correct? This calcium chloride molecule is made up of 1 calcium and 2 chlorines. So the mass of the molecule is going to equal the sum of the mass of the elements that make up the molecule. When we add these up together, 5 and 5 is 10 and 1 is 11. Carry the 1, 5, 10, 11. Carry the 1, 5, and 6 is 11. 111.1 AMU. My precision is to the tenths place, and we're already in the tenths place, so we're good. What that means is 1 molecule of calcium chloride has a mass of 111.1 AMU. Because I know the mass of one molecule, what do I also know? In terms of mass, if I know the mass of a molecule, I also know the mass of a mole of the molecule, right? The mass of the molecule is 111.1 AMU. The mass of a mole, then, is equal to what? Go ahead and tell me. 111.1 grams of that molecule. So the molar mass, we write it over here, the molar mass of calcium chloride is equal to 111.1 grams. One molecule is 111.1 AMU, so 1 mole of the molecule is 111.1 grams, changing the units from AMUs to grams when I up it to a mole's worth. So then it's just going back to the diagram here and saying, okay, the mass is equal to the moles times the molar mass equals mass, right? I'm trying to solve for the mass. Mass is equal to moles times molar mass. The number of moles, I've been given 0.344 moles, multiplying that by 111.1 grams per mole. Check my units real quick. I have moles. Over here I've got moles divided by moles. They cancel. I'm left with grams, and that's what I was asked for. So I do the math. 0.344 times 111.1 is 38.2. 38.2 grams of calcium chloride. Okay. Other than just need to practice, any questions on how we solve that problem? Or the procedure, or how to compute all the different steps? If not, we're going to roll on to 8. Number 8, a sample of potassium chloride. Okay, before we go anywhere, potassium chloride. What is the formula for potassium chloride? Okay, the symbol for potassium is K, and for chloride or chlorine, ide is the ionic form of ene, right? Chlorine is Cl. The question is, are there any subscripts? Potassium. Where is potassium on the periodic table? Potassium is a column 1. It wants to become a positive 1 then. Chlorine is a column 7. It wants to become a negative 1. And so potassium chloride, just like sodium chloride, is a 1-to-1 relationship. So this is the formula for potassium chloride. 1 potassium combines with 1 chlorine, because potassium has a +1. The potassium ion has a +1 charge. The chlorine ion has a -1 charge, so they match up 1-to-1. All right. And so the question then for 8 is, a sample of this potassium chloride has a mass of 25.0 grams. So our mass of potassium chloride is equal to 25.0 grams of potassium chloride. How many moles is that? Moles of potassium chloride equals what? Okay. If you remember from our bridge diagram, we're going to be using the same kind of relationship, mass to moles. In this case, we're going to have a mass, we're going to moles. Over here we have a mass, we're going to moles, right? So moles is equal to mass divided by the molar mass. Do you see that from the bridge diagram? Moles is equal to mass divided by molar mass. We're looking for moles. We've been given mass. We don't know molar mass. So let's figure it out. Because we're looking for this, we've got this, and we need this. The molar mass for potassium chloride. The molar mass for potassium chloride, first of all, let's look at the mass of one molecule of potassium chloride. It would be the mass of one potassium and the mass of one chlorine atom. Potassium has an atomic mass of 39.1. AMU. Chlorine has a mass of 35.5 AMU. And together, they have a mass of 74.6 AMU. 74.6 AMUs is the mass of one molecule of potassium chloride. Knowing that one molecule of potassium chloride is 74.6 AMU, we also know then that the molar mass, or the mass of 1 mole of potassium chloride, is 74.6 grams of potassium chloride. So in this problem, our moles of potassium chloride is equal to 25.0 grams divided by 74.6 grams per mole. And again, trusting the key to do the computer or the calculator skills, 0.335 moles of potassium chloride. You should be able to look at that and say, hey, you know what? It is just about 1/3, right? This is almost 75 and this is 25. It's about 1/3. It's about 1/3. Okay. Let's try to do 9. And right now, my intention would be just to pick up where we leave off here Monday in class. Okay? So we'll just finish it after that. Number 9. How many grams are contained in a 9.02 mole sample of carbon dioxide? Hopefully we know that carbon dioxide, we've seen it so many times, is CO2. And moles of CO2 is 9.02. Moles of CO2 is 9.02, and then how many grams? So the mass of CO2 is equal to how many grams? So again, looking at the diagram, we've got mass, moles, we've got to convert from moles to mass. So the mass is equal to the moles times the molar mass. The mass is equal to 9.02 moles times whatever the molar mass is of carbon dioxide. Carbon dioxide's molar mass is equal to the mass of 1 carbon and 2 oxygens, 12.0 and 16.0. We've got 2 of them. That gives us a mass of 12, 13, 14, 1 to carry the 4, 44.0 AMUs per molecule. 44.0 AMUs per molecule also tells me that it's 44.0 grams per mole, and that's my molar mass. So 9.02 times 44.0 grams per mole is going to equal 397 grams of CO2.